There you go. All right. I'll get started. Heavenly Father, we thank you for this day. Again, I thank you for this class and this time we have to study your creation. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so have an example I should work here. So here's the example. Suppose you've got the Earth. Right? And
is this diagram the scale?
No. So then over here you got satellite, all right? And that satellite is, let's say, distance r from the center of the Earth. Then the question is this. What altitude must a satellite orbit to achieve geosynchronous orbit? What's geosynchronous orbit? Free to correct my spelling, I don't care. Go for it, but I should have just everything. So question, what does it mean, geosynchronous?
It orbits at the same speed as the ground under it.
Yeah, it stays at the same position relative to the ground underneath it.
Okay, so like if, so maybe this is the North Pole right here, right? Like the North Pole sticking out like here. And then if we could track the satellite, the spot on the Earth, like here, that point P would be over here when the satellite was like over here, right? Anyway, whatever. So the question then is, how do you achieve geosynchronous orbit? Like what makes the satellite go in geosynchronous orbit? So we are ignoring gravity from the moon, we're ignoring gravity from other satellites, we're ignoring gravity from the sun. The only gravity we're caring about is Earth's gravity. Yep.
What would it look like if it wasn't geosynchronous? Would the R not be constant?
Well, I suppose there are all kinds of different orbits that are possible. Like not all orbits around the Earth have to be circular. You know, we could have like an elliptical orbit or something.
Is that what the property of being geosynchronous is?
Well, no. I mean, there are geosynchronous means it's a circular orbit, and also the period of the orbit is what?
1 day. 1 day.
1 day. So that's what uniquely defines it as geosynchronous. So yeah, I mean this means the period of the orbit is 1 day, right? Or if you like, 86,400 seconds. That's 24 times 3,600. Why do I know this? I don't know. It just stuck in my brain. Okay, so number of seconds in a day is 86,400. Now what keeps the satellite in geosynchronous orbit is that the force of gravity, right, which is gm, mass of the satellite, mass of the Earth, right, divided by the radius of the Earth squared. That's the force of gravity here. It's center seeking, right? So like if I was to draw a three-body diagram, it's really kind of boring. It's just this, right? And there it is, that force of gravity center seeking. And it's giving us the entire necessary force to achieve the centripetal acceleration that we want. Namely, little m v squared over, oh, and I said RE, that's nonsense.
It's R plus R.
Oh yeah, I was just going to say R squared, and this would be R. But you're right, we could say R is equal to RE plus H for altitude. I usually use H for altitude. Okay, great, then what? Well, the mass of the satellite apparently doesn't matter, right? Which is only true to a certain point, right? Like if the mass of the satellite was the mass of the Earth, it would very much matter, and this would be a ridiculous approximation. This only makes sense in as much as the mass of the satellite is inconsequential compared to the mass of the Earth. In which case, the center of mass of the satellite Earth system is essentially in the middle of the Earth, to a very good approximation. Anyway, so the masses, they be canceling, and we've got, looks like G, mass of the Earth, divided by R equals V squared. Now well, V squared, what's that? That is also known as 2 pi R divided by the period quantity squared, right? So then what? Looks like we've got G, mass of the Earth, divided by the radius cubed, I mean the distance cubed, right? And that's equal to 4 pi squared over t squared. So let's solve for R. What do we got? R looks like is going to be the cube root of G times the mass of the Earth times period squared divided by, please close the laptop. I hear too much clicking. Thank you. So G, mass of the Earth times time squared divided by 4 pi squared. All right. Do you guys agree? Uh-oh. What was the mass of the Earth? So to a decent approximation, 5.97 times 10 to the 24th. So we got here, and G was 6.67 times 10 to the minus 11 times the mass of the Earth, which was about 5.97 times 10 to the 24th. And then we got the number of seconds in a day, 86,400. Square that. Divide all of this by 4 pi squared and take that to the 1/3 power. What do we get? So the annoying thing is, this is the only radius that you can achieve geosynchronous orbit at, right? So if you want your orbit to be a day, this is where you have to park your satellite, right? Which means that there's a lot of satellites at this particular radial orbit, right? I mean, there's a lot of real estate out there, I suppose, but still, you can see how it might get crowded. There's a lot of space in space. All right, let's see here. 6.67 times 5.97 times 86,400 squared divided by 4 divided by pi squared times 10 to the what? 24 minus 11 is 13. And then I got to cube root all that. All right. See if you guys agree with me. I've got R is 1, 2, 3, 4, 5. Looks like 42.2 123 times 10 to the, I know that's weird to do 42. Just a second, let me think about this. 1, 2, 3, 4, 5, 6. Well, yeah, okay, fine. That's times 10 to the 6th meters. Now, what was the radius of the Earth, we said? The mean orbital radius is something like 6 point...
At least a kilometer.
At least a kilometer? The radius of the Earth was 6.371 times 10 to the 6th meters. So about 6,000 kilometers, 6,300 kilometers, about 6,371 kilometers. So I need to subtract basically 6,371,000 from that, and that gives me h, which is equal to r minus the radius of the Earth of 35.86 times 10 to the 6th meters. So that's the altitude we're talking about. What is that? So if we were to take the 42.23, and divide by 6.371, that gives you some sense of it. It's about 6.6 Earth radii out in terms of altitude. Well, excuse me, it's about 5.62 Earth radii in altitude. So it's pretty far out there as it goes. What would that be in terms of miles? Yes?
At least 10.
At least 10?
Honestly, maybe it would be.
Let's see here. I think about 22,000, it's approximately 22,287 miles. Of course, these are not all significant, but that's geosynchronous orbit, something like that. About 22,000 miles. Now, so to answer your question, which I think you're starting to ask, which is like, is this how satellites actually orbit? And the answer is sometimes, but not all of them. I think a lot of the communication satellites are based on like overlap. They've got a bunch of different satellites that are overlapping, and they've got more like maybe a 90-minute orbit or something like that. They're on like a faster, closer orbit, and there's just like a lot of them overlapping, something like that. Because it's kind of a pain to get a satellite out that far, right? For one thing. It's doubtless easier to place satellites a little bit closer to the Earth. But obviously, this would be a very advantageous thing because you'd always have that like fixed shadow if you're using it for communications purposes. It'd always be there. But I guess on the downside, you actually have the time of flight for the radiation, which, excuse me, is something. It's not much, but I mean, light is very fast. So, okay, any questions? Okay, so here's another example. Suppose sometimes you have a pair of planets. So here's like M, another planet M, and let's suppose they're equal mass. All right, and one possible configuration is you have a pair of equal masses that are orbiting in like a circle around a common center point, right? So then the question then is, how would the radius be related to the speed of the orbit here? What could we say? So there are actually some systems like this where you have a pair of stars, which are like, well, not a pair of stars, I should say. I think a pair of planets that are orbiting. Oh,
No, it's stars.
it's stars? Binary stars, that's right. Yeah. I'm trying to envision it. Well, the way they're orbiting is such that the intensity of the star varies, comes and goes, so you can kind of see what the period of the orbit is just from looking at the intensity, the waning of the intensity of the light, the observed starlight from such a binary system. So these things are actually observed. I did a laboratory on it in graduate school, which was wonderful because we were supposed to go and like take new astronomical data from like the telescope on the rooftop of the building, but the weather was always bad. So I just got to use the data which was sitting in the computer, which made it a good lab in my estimation. It was a lab where I didn't have to do the lab. Anyway, so what keeps these two masses orbiting around the center, that was supposed to be a circle, is the force of gravity, right? And force of gravity from what? So this one, has the force of gravity from the other one, right? And like vice versa, down here, this one, like that. So it doesn't really matter which mass you pick one or the other, and then we can analyze the motion using Newton's law again. So we have the mass, it's force of gravity, right? So G, M divided by, now what's the distance? What's the distance between the gravitating objects here? 2r, right. So I take 2r, I square it, and that's equal to what? M v squared. Now this is, I don't put 2r here, right? Because it's circular motion with radius r, so I just have r. And, okay, so then we can work it out. So we have m over r times 2 pi r over the period. Well, okay, I guess it depends on what I'm after here. Well, let me just stop this for a second here. So we can find the velocity as it relates to the radius in the orbit here pretty easily. Cancel m, and this says that v squared is g times the mass divided by 4r, right? Because the r squared cancels with the r there. And so we got is that the velocity of such a system here is given by g times the mass of the planets or stars which are rotating around each other, orbiting around each other, times 4 times the radius of the orbit. Now, of course, we can also derive what's the relation between the period and the radius of the orbit, right? How would we do that? So, like, to get that, find relation between the period of the motion and the radius. Since it's circular and it's constant velocity, constant speed rather, I should say. Velocity is not constant, it's always changing. We got 2 pi r divided by the period is equal to square root of gm. I mean, you could have jumped back up here and do the algebra wherever you want, but I'm picking up where I left off there. So if we square both sides, what you got? You got yourself 4 pi squared r squared divided by the period squared is gm over 4r, which that tells me that r cubed is equal to gm t squared divided by 4 pi squared, which finally tells me that the radius is in fact the cube root of gm t squared over 4 pi squared. So there you go. That's the relation between the radius and the period of the orbit of a binary system. Yeah. Any questions? What if there were 3? Well, I mean, you guys, your choice. What do you want to do, 3 or 4? 4? Okay, cool. So suppose we got 4 equal masses. And they're all rotating around a common circular center. This is a possible orbit, right? Then we can try to derive what's the velocity as it relates to the mass and the radius, as well as the, formula that relates the radius to the period, just like we did over there. So m, 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 m. All right. Now you notice I only analyzed one of the stars in the previous example, right? I didn't do Newton's law for both of them, did I? It was enough to just do it for one. Why? It's a symmetry, right? Because it's the same for one as it is for the other. And the same thing is true here, right? So I just need to look at Newton's law for one of the, what do you guys want to make it? Stars? Let's make it moons. 4 moons. All right. Well, I mean, and the planet has been blown up by evil cats or something. I don't know. So if you like, we could add you want me to add a planet? We could add a central planet if you'd like. No? Okay. It doesn't really make it much different. Add a planet? Okay. Do. We'll make that one big M.
Yeah.
There we go. So we can pick any one of the masses, except for the center one. Obviously, that one's not even. We're essentially just thinking of that as being fixed at the center. The center of mass is at the center of the big M. So I think for the purposes of my artistry, let's think about the free body diagram on the upper one. All right. So this distance is r, and I'm going to use capital R because I'm tired of lowercase r at the moment. It's not a terribly deep reason, but it's a reason. So this distance right here is r, and this distance here is also r, but also kind of irrelevant. Okay, so let me just draw the forces up on the upper mass. What are they? We've got the force from big M, right? And let me just number these. 1, 2, and 3. So I've also got the force of gravity from 2 this way. I've got the force of gravity from 1 this way. I've got the force of gravity from 3 that way. Gravity is a vector, right? We haven't had to think about vectors in the previous problems because we got lucky, right? But generically speaking, we do have to think about the vectorial nature of gravity. It can cancel out. It doesn't just have to add. Let's see here. So, of course, what happens here is that the let's say the right part of F3 and the left part of F1, they cancel, right? So the net force on M, I guess I'll call it 4. If that's 1, 2, 3, this must be 4, right? So the net force on 4 is downward, center seeking, right? And so how do you figure out what's the angle here? If I connect these along the center of mass, which is what I should do, what's the angle there? 45, right? You guys see that. What if we had 3 masses instead of 4? That angle wouldn't be 45 anymore, would it? It'd be 60, yeah. You'd have to think about it. So this is 45 degrees. So if we think about this, the net force should be, let's see here, let me do the easy one. G M big M, this distance is the radius squared. All right, plus what? Plus G little m, I'm going to do F2 now. How far is that? Twice the radius, right? So I do 2r. Because this is F2. You know, Fm, force from 2. And by symmetry, we can just double the 1 for 3, right? So let's just do twice G, M. Ooh, what's the distance? What's the distance between like 1 and 4 or 4 and 3? How far is that?
Square root of 2r.
Square root of 2r. Do you guys see why? Does that make sense? So this is a right triangle. So the hypotenuse is the square root of r squared plus r squared, which is square root of 2r. So we've got the square root of 2r squared. And that's not it, though. We don't have the full magnitude, right? Because the horizontal parts of it are canceling. We have to pick out the vertical component, so we have to multiply that by what? Like cosine of 45 degrees, or if you prefer sine of 45 degrees. It's like up to you. That's a joke, but the same. Sorry. I'm amused. I'm easily amused. Actually, I should not laugh, because laughing will make me cough. So, like a lot. Where are we? I think that's it for the forces. And so, of course, all of this is just equal to mv squared over r, because it's going in a circle. So that has to be the net force is mv squared over r, as we derived back in the day. So the m's there are canceling, and you can factor a g out. You got yourself a big G, and 1 over r squared, sorry, my bad, m over r squared plus little m over 4r squared. Let's see here. Plus little m, let's see here. I'm going to write, so we've got times 2 divided by 2 r squared. That's just from this and that. 1 over root 2 for my cosine, close my parenthesis, equal v squared over r. All right. So I have g over r times apparently big M plus, let's see here, I've got a quarter, 1/4 plus 1 over root 2. Is there a mistake?
Shouldn't you have factored on our square?
What square?
Never mind.
Oh, okay. I mean, I do make mistakes. So I multiplied the r, and this is all equal to v squared, so I'm going to square root this thing, and just there. So there's the velocity as a function of the masses and the radius here. The more tight the radius, the smaller the radius, the faster the velocity of such an orbital system, right? The larger the radius, the slower the velocity. Yeah? Is there a question? Huh?
In the denominator up top, why is it root 2 r squared?
Oh, okay. So that's because the force of 1, for example, is equal to g, m, and then the distance from like 1 to 4 squared. So like, that's the total magnitude. So like the distance is square root of 2 times r, because it's the hypotenuse of the triangle, you know? So that's why we had that there. And then the cosine is because we're just picking up the vertical component of it, which adds. The horizontal part cancels with the F3. And then, of course, if you want to find the relation between the period and the radius, you just set this equal to 2 pi r over t, and you can solve for it, right? I won't bother because I'm getting tired. Questions? No? Okay. Yeah?
So, okay, so we were finding that for the system without the and we just ignore the first.
So yeah, if the planet weren't in the center, then the term with the big M would be gone, but everything else would be the same. I once gave a final exam where I let the number of moons go to infinity. I wanted to see if Min could solve it. He sort of did. But it turns out that that problem, as I had it stated, it was kind of unphysical. Well, I was thinking you could do something like derive like the equations of motion for like the rings of Saturn or something from this idea, something like that. But in order to make that sensible, I have to, when I take the limit as the number of moons goes to infinity, I can't have the mass of every moon fixed at a finite amount. I have to decrease the amount of mass for each moon as I increase the number of moons, so that the net mass of all the moons is held constant. I wasn't doing that. It's what made it unphysical. So, but anyway, that was a bonus question, obviously. You know? Oi. So one of you guys asked me a question today about the mastering homework, which I thought I should share with the rest of you because it is subtle. So I'll help you guys out. Which one was that? Yeah, the one we were talking about.
Problem 9.85.
9.85. So, yeah, this one's kind of funky. 9.85, if I can find it. I won't work it all the way out, but I'll just kind of give you guys a significant hint about it. See, because this problem, you're given a sphere that has variable density. Problem 9.85. So roughly speaking, you've got this sphere, and the density is equal to something like a constant A minus another constant times R. Here, A and B are given numbers in your problem, okay? And the question asks two things, the one of which I think you all will get without me helping you, but I'll help you anyway, which is that the density, so the first question is to calculate the mass, all right, and the radius is also given. All right, so the radius is given in this thing too, like the total radius. So density is equal to mass per unit volume, right? And so because the volume is a function, the density is a function of the radius, so if I say look at this like a shell, a spherical shell at radius r, then the little bit of volume from such a spherical shell is given by dV is 4 pi r squared dr, right? That would be the volume of such a shell. And so dm, I could calculate from rho dV, which in this context would be rho times 4 pi r squared dr. And of course, you take this formula up here, right? And you plug it in down there. You integrate from r equals 0 to the given radius. And that will calculate the mass, if you do it carefully. Some people have already done this? Just one person? Okay, well, if it worked for one person, there's good odds that it'll work for the rest of you. So then the much harder question is part B. It says, calculate the moment of inertia for this sphere. And that stumped me for a little bit today, until it finally dawned on me that we can use my suffering in the notes. See, in my notes, I prove that the moment of inertia of a spherical shell, right? So if we have like just a shell, that if this had mass m, the moment of inertia for it would be 2/3 mr cubed, right? That's the moment of inertia for a spherical shell. As compared to what? For a solid sphere, it was what? 2/5, yeah. So 0.4 versus 0.67-ish. Because, of course, more of the mass is further away from the center of rotation, so it's got a larger moment of inertia. So the thought I had was I could use that example to calculate the moment of inertia of this by slicing it into spherical shells. The trouble with this one is I can't use the derivation that I have in the notes for the solid sphere without significant modification. But I can basically just bootstrap this example using the spherical shell in the following way. So if I think about this spherical shell, right? All right. This shell here, what's the mass? What's the mass in the shell? Well, we just wrote it right here, right? This is the mass in the shell, right? At r. So what's the moment of inertia for such? So di would just be what? Rho. Just this right here. So we do 2/3. Why did I put a cube there? Come on, guys, don't let me do that. Good grief. Boy, man, that's not good. All right, 2/3. And then dm, because it's a little tiny little bitty mass spread out over this infinitesimal shell, right? dm times r squared. But that means 2/3 times rho times 4 pi r squared times r squared, and I put the dr last. And of course here rho is the a minus br I talked about at the start. So, you know, we've got something like 8 pi over 3 times a minus br times r to the power 4 dr. And then that's just the moment of inertia for one of the spherical shells as a function of the distance from the center, right? And then you just simply integrate that from 0 to r, and that should, is that what we did? Okay, because I think I derived it a weird or different way for you today, didn't I? Like I did something with sigma.
You started to, and then you went back and did it this way.
Oh, okay, good. I've forgotten. So, yeah, I think when I assigned this homework problem, I was thinking it was like more in tune with what, I was thinking it was more like a different problem. I wasn't intending quite all of this. But anyway, with this hint, it becomes a relatively easy problem. You just have to, again, kind of make use of the other example in my notes. Now this right here does require deriving this requires honest to goodness Calc 3 calculation, because it involves the like interplay between cylindrical and spherical coordinates, which is a little bit outside our scope in here. But it is inside our scope, very much inside our scope, to know that the moment of inertia for a spherical shell is this, and to use it in this kind of way. Like that is very much part of this course. So anyway, if you guys have other questions about homework, feel free to ask. So I'm probably going to cancel office hours today. I'm kind of low energy. I think I need to go home. So if you got questions, now would be a good time. Nobody? Yeah.
How do you find the moment of inertia of a square being rotated around the corner?
A square being rotated around the corner. Ooh, is that a problem I assigned you?
It's part of the mission.
It's on the mission?
I don't remember where it's at. It's part of something.
Huh. A square around its corner, huh?
Well, yes, with different forces on each corner.
Yeah.
Now where's it rotating?
It's rotating around one corner, and then there's a force on each of the other forces. It's problem 51.
Oh, I've left that back in my office. I'm an idiot. Yeah, if you, let me steal it from you for a second.
I haven't written anything on it yet, really.
You're fine. So it's uniformly distributed, square pivots around point A. Okay, so I'm trying to think. Do we have? There may be a formula for the moment of inertia of like a planar rectangle around its center of mass in the book, for example. One way if we had that. Yeah. Shush. I said shush. Quiet. United States Postal Service. Well, that's odd. All right, anyway. Yep.
Could we possibly average the distance of the far edges of the square and use that?
I don't think so. I mean, so, all right, so I think that the problem is that it's not just a linear average. The moment of inertia concerns the square of the distance from the pivot point. So you're getting much more moment of inertia from like the far corner of the square as opposed to the part that's really close to the pivot point contributes nearly nothing to the moment of inertia, right? So like the further away it does, the more. Like I was just saying, I think in the book, I think one of the standard moments of inertia that we know is the moment of inertia of like a rectangular region about its center of mass. Am I right? No one has a book? Of course not. Unfortunately, I have the book, but I have the chapter on momentum, which is not helpful to us at the moment. I need the the rotation part. What I'm getting to is if we know the moment of inertia of a square, we can use the parallel axis theorem, because like the moment of inertia for the square is obviously, the center of mass is obviously the center of the square, right? So if we're rotating around there, we could use the parallel axis theorem to find the moment of inertia of a square about about the corner. Well, yes, I know that, but stupid double. No. I'm trying to. There should be like a table, moment of inertia calculations, maybe. They should have a summary. I mean, we could work it out, but I don't think you guys want. If we can not work it out, you'd like that, right? Yeah. Man. Well. Now the other possibility is try again here. Oh, okay, so listen, we're going to have to think about that. How do we find the moment of inertia? Oof. I was thinking about dividing it into little, like this, you know. But then it occurs to me that once we get out to here, past that point, it gets really kind of annoying in terms of like how much.
You could find the torque for each separate corner and then have them.
Like, I mean, maybe we could do like this,
And these polar coordinates.
maybe something like this, perhaps. But that's not. See, I don't know about that either because I'm a little bit leery that they're not. It's not quite a whatchamacallit. I don't know. I'm going to have to think about how to calculate this, guys. I can't do it in 2 minutes, unfortunately. All right, so once we find the moment of inertia, though, how do we solve the problem? So once you find the moment of inertia, you've got the pivot point is A, right? And you've got forces which are given. Yeah? So solve the motion. You just set the moment of inertia times angular acceleration is equal to the net torque. What's the net torque equal to? Well, that should be relatively easy to figure out. I tell you the forces, right? They're applied at particular points. You can figure out the radial arms, each one of those points. And so you can calculate the torque, right? So I think that the complicated thing here, and we'll circle back to this next class, all right? Like I'll try to work it out for you guys. Is what's the moment of inertia for this square, right? That's not, to me, that's not obvious. Maybe I'm missing some simple trick. Maybe you guys could talk me into it. But I don't. What's that? Nah.
It does by the square, it's because of this.
I heard Kate knows how to do that.
You could take the average.
Who knows?
Kate can explain it for me.
Okay.
Take the square root of the average
Square root of the average.
of the square. So
Yeah.
It takes me 3 minutes to do it, but we only have 2 minutes.
You do it in 3 minutes, but we only have 2. Now we only have 1. Now we have none. Oh no.